The Earth is a magnificent, integrated physical system. We've seen that the stately convection of rock in the planet's deep interior drives plate tectonics, and plate tectonics, in turn, governs the positions of continents, as well as the distribution of earthquakes and volcanoes, ore deposits, and all sorts of other geological phenomena. The Earth can also be viewed as an integrated system in other ways. Our planet is a great and complex collection of atoms that are constantly moving and reorganizing themselves as the Earth undergoes change. Lecture 40 is the first of 3 presentations that will examine the great cycles of Earth's water and its air and its rock. And we'll see that the Earth's store of water is essentially unchanging. The same molecules are recycled over and over again. I have 2 main objectives here. I want to first focus on the general concept of Earth's geochemical cycles. These principles apply to any collection of atoms or molecules on the planet. Then for most of this lecture, I'll consider the water cycle. That's a remarkably dynamic cycle that's essential to geological change and to life itself. Finally, I'll look at some of the ways in which humans are altering that natural cycle. The plate tectonics revolution has provided us with a new appreciation of the Earth as a remarkably dynamic planet. The crust is constantly being created and destroyed and reworked as the thin, brittle lithosphere is shunted around by the mobile plastic asthenosphere. New crust is being formed constantly at divergent plate boundaries, especially along mid-ocean volcanic ridges. Basaltic magma comes out to the surface and flows out to either side, making a symmetrical system on the ocean floor. Then old crust is swallowed up by subduction at convergent plate boundaries. That usually involves at least one oceanic plate that plunges down into the mantle. These subduction zones are often the sites of earthquakes and chains of volcanoes. And as these great tectonic plates move past each other, they define transform boundaries, where many of the Earth's largest earthquakes occur. This whole process of plate tectonics, by which the Earth's crustal material is constantly recycled, is a grand example of Earth's cycles, which are the subject of the next 3 lectures. Every material object we use in our lives, every solid, every liquid, every gaseous substance, it comes from the Earth. Wood, water, metals, plastics, what are called all natural materials, and also man-made materials as well. All are formed from atoms that came from the same vast, though finite, reservoir. To be sure, there's small amounts of material that are being added daily from small meteorites and perhaps small comets, but this is tiny. This is an inconsequential amount of mass compared to the huge mass of the planet. Basically, what you see is what you get. But the good news is that all those atoms can be used over and over and over again. The Earth is the ultimate recycling machine. Every element, every chemical compound on Earth can be described in terms of a geochemical cycle. Now, a geochemical cycle is basically a story. It's about the locations and the movements of a particular substance. So you can talk about the geochemical cycle of life's essential elements like carbon and phosphorus, or of resources like iron or copper, or even the chemical cycles of pollutants like mercury and lead. Now, the description of a geochemical cycle involves 2 key types of information. First, you need an accounting of all the different repositories or reservoirs of that element or compound. Now, a reservoir in this context is just a physical situation in which that material spends some period of time. So, reservoirs of water, they include oceans, and they're clouds, they're rivers and streams. Glaciers are reservoirs, and so forth. By the same token, you can have reservoirs of gold. They include natural deposits such as stream gravel and their quartz veins, as well as human-made repositories in bank vaults and jewelry stores. Okay, so that's reservoirs. And then you need to document the processes by which the substance moves from one reservoir to another. Again, that could be a completely natural process, or it could be a process that's the result of human technology. The geochemical cycle of the element gold provides a really good example of what I mean. Okay, first, the reservoirs of gold. The major known gold reservoirs include, for example, the oceans. Now, that might seem pretty surprising, but every cubic kilometer of the ocean contains about 50 kilograms of gold. That's a huge gold reservoir if anyone could figure out an efficient way to extract it. Now, lots of gold is also dissolved in hydrothermal fluids. This kind of gold deposit is especially common in subduction zones. That's where fluid comes from the mantle. Recall that as crustal rocks are subducted, they heat up, then they partially melt, and the resulting magma is rich in water, and that water dissolves lots of metals, including gold. So these hydrothermal fluids are a significant reservoir of gold. And then a lot of gold is locked up in metal ore bodies. Those are in rocks, especially rocks associated with subduction volcanism. This gold reservoir is, of course, closely tied to hydrothermal fluids. Now, a lot of the gold that's been mined since prehistoric times, that comes from gravel and sediments and streams. They're called placer deposits. That's the kind of gold reservoir that triggered the California gold rush of the 1850s. And then humans, they worked fanatically to create new gold reservoirs in bank vaults. And we'll see throughout this lecture that human technology has the potential to affect geochemical cycles in pretty dramatic ways. Okay, that brief catalog of gold reservoirs is the first step. Now we need to identify the various processes that gradually move gold atoms from one reservoir to another reservoir. And I've sort of introduced some of these already. For one thing, erosion by wind and water gradually fragments and dissolves rocks and soils, and that process leads to the release of gold particles. So gold is transferred from solid rock to stream sediments. And then hydrothermal fluids. Those fluids rich in gold can eventually reach the oceans, and that kind of transfer is responsible for that surprisingly high gold content of the oceans. And then hydrothermal fluids also transfer gold to rock veins. So the hydrothermal activity associated with volcanoes may first concentrate gold in solution, and then as those fluids migrate upward to the cooler parts of the crust, the gold atoms precipitate out of solution and they're deposited in an ore body. And then, of course, human activities. They can affect geochemical cycles by transferring gold from a natural reservoir to a man-made one. So over the centuries, humans have extracted large amounts of gold from ore bodies and placed it in vaults and in jewelry and so forth. And then some of that gold becomes scratched, it becomes abraded, and lost. So those gold atoms then return back to the soil. It's often true that new technologies may alter a geochemical cycle. You know, it's not yet economical to extract gold from ocean water, but someday it might be. Now, there are literally hundreds and hundreds of individual geochemical cycles to study. Every chemical element, both metallic elements and non-metallic elements, has its own geochemical cycle. So there are scientists whose research specialty is the geochemical cycle of boron or uranium or argon or tungsten. All kinds of small molecules also have geochemical cycles. Now water, that's H2O, is the most obvious example. But some scientists study the geochemical cycles of ammonia, that's NH3. And then there's carbon dioxide, CO2, and even ozone, O3 molecules, for example. And geologists extend these ideas to the geochemical cycles of many different minerals. The common mineral quartz, for example, that's very important. Quartz is silicon dioxide with 2 oxygen atoms for every silicon atom. It forms initially from silica-rich magmas or from hydrothermal fluid, and it often forms the rock in the rock granite. You can see individual quartz grains in granite. Here's an example from Pikes Peak, and the quartz are these colorless grains that you see throughout that piece of granite. But when the rocks weather, the resistant quartz grains form stream pebbles and sand grains. They form most of the sandy beaches at the shore, and then sediments get reformed into sedimentary rocks like sandstones, which cement the same quartz grains. And then the sandstone can weather, so individual grains go through the cycle through many, many generations of sand and sandstone. But in a broad sense, 3 major Earth cycles are of primary concern. First is the water cycle. That's so critical to life on Earth. That's the main subject of this lecture. Then there's the atmospheric cycle, which considers all the gases of the atmosphere, as well as the short-term cycles of the weather and the much longer scale cycle of climate. And then the third great cycle, that's called the rock cycle. That's the subject of lecture 42. Now, though these are quite different in detail, these cycles share 4 common characteristics. First, all of these cycles involve the movement of matter among several different reservoirs. For atoms or molecules to cycle, they have to move. And second, all these cycles are driven by energy. Energy from the earth, energy from the sun. Nothing happens without a force, and it takes energy to do work, to exert force over a distance. The third common characteristic of geochemical cycles is that all of these cycles can be altered by human activities. Human technologies have gotten very sophisticated in altering natural geochemical cycles. And finally, fourth, all of these cycles are complexly interrelated. Now, we saw that with the geochemical cycle of gold. Gold atoms are inextricably tied to the rock cycle and to the water cycles. Okay, now to the geochemical cycle of water. Water has played and continues to play a unique role in the geological and the biological history of Earth's environment, especially the environment near the surface. The Earth's water cycle is sometimes called the hydrological cycle. It deals with the reservoirs and the movements of water molecules. And that's whether they're in the solid form of ice or liquid water or in gaseous water vapor in the atmosphere. So we need to inventory all the different reservoirs of water and then document how water moves from one reservoir to another. But first, I want to establish that the Earth's water budget is almost completely closed. Now, very little water escapes into space by gravitational loss, and only a minor amount of water arrives from space by way of comets and meteorites. Now, you might recall the controversy that was raised by Professor Louis Frank of the University of Iowa. Remember, he claims that small comets are constantly raining down on Earth, and this adds a non-trivial amount of water, according to him. Well, the jury's still out on that one, though I think it's fair to say that the great majority of experts aren't convinced of Frank's claims. So depending on how you count reservoirs, there are 6 or perhaps 7 major repositories of water on Earth. So the reservoirs that are accessible from our vantage point on the surface include, first and foremost, the world's oceans. That's by far the biggest single reservoir. And then next in size comes ice caps and glaciers. That solid water is the second largest repository, and its size is highly variable over long spans of geological time. And then freshwater lakes and rivers constitute a third important reservoir. It's not very large relative to oceans, but it's really important to humans because it's freshwater. And then we have groundwater. That's actually a vast network of subsurface repositories. It's also of extreme importance to human pursuits. Then we have the atmosphere. The atmosphere holds a relatively small amount of water at any one time. From a purely human perspective, one of the atmosphere's principal roles is as a way to purify and to transfer water from the oceans to the land. And it turns out that living organisms are yet another water repository, albeit a very minor one. So that's 6 obvious reservoirs near the surface. There are actually 2 other potentially vast storehouses of water in the Earth, but they're not very accessible to humans, and we're still trying to learn about how much influence they really have. Now, one of these is hydrous minerals. Those are minerals that incorporate water molecules, or in some cases, protons, H+ or hydroxyl OH- groups, and those are incorporated into the crystal structure. Now, integrated over the entire crust, these minerals hold huge amounts of water. And then there's also the role of the mantle in the water cycle. Now, recall from the last lecture that subduction carries lithosphere of wet rocks deep into the crust and even into the mantle. If even a small fraction of this subducted water becomes locked into high-pressure minerals, then the mantle might hold many times the total accessible water of the surface. By some recent estimates, all the water of the ocean cycles into and out of the mantle over and over again on a scale of a few 100 million years. This water, furthermore, must slowly recycle to the surface through volcanism at the ocean ridges, above subduction zones, at hot spots. So it's axiomatic that what goes down into the mantle must eventually come back up. Okay, let's look at these reservoirs in a bit more detail. By far, the largest accessible reservoir of water is the oceans, which now hold almost 98% of all accessible water. Oceans now cover about 3/4 of the Earth's surface with an average depth of about 2 kilometers. That's more than a mile deep. Take a look at this globe. I especially like the view that's centered on the Hawaiian Islands. Just look at how much water there is on the surface of the Earth. One of the most obvious and distinctive aspects of the oceans is that they're salty. Well, as we saw, water is a polar molecule, so it's an excellent solvent of ionically bonded salts. See, water gradually dissolves various elements from rocks and soils, and these solutes wind up in the oceans. Over billions of years of geological time, the oceans have thus become salty. The principal elements in solution include sodium and chlorine. Those are the elements of the commonest kind of salt, sodium chloride, table salt. Then there's calcium, magnesium, potassium, and lots more. There's also a fair amount of sulfur dissolved as sulfate too, so calcium and magnesium sulfates also appear as minerals when ocean water evaporates. And then there are lesser amounts of dozens of elements in seawater. I already told you about gold, 50 kilograms per cubic kilometer. The ocean is an important part of the geochemical cycle of these and many, many other elements. So you can see how different geochemical cycles are interrelated. The ocean's just not a repository of water. It has many other elements as well. Okay, glaciers, ice sheets, other forms of solid water. They now contain an estimated 2% of all Earth's accessible water. Now, most of this ice covers the land masses of Antarctica and Greenland, and the rest occurs as thin coverings of the polar oceans and widely scattered mountain glaciers at high altitudes. Now, this is a key point. You can pile up huge amounts of ice on solid land, but relatively little ice can build up on the open ocean. So the amount of ice at any one time in Earth's history depends on the positions of continents. As we'll see shortly, the distribution of water between oceans and ice reservoirs can change dramatically and with profound effect on the world's ecosystems. That depends on the global climate. So fresh water at or near the Earth's surface of land accounts for at most about 0.4% of all accessible water. And of this amount, more than 90%, by some estimates as much as 98%, is stored beneath the surface as groundwater. They're huge underground reservoirs. They're formed by porous rock layers that are sandwiched between impervious layers. And here's how that works. Rain falls in the mountains and then it percolates into the ground. Water finds a bed of rock that's porous, and so the water saturates that bed, and gravity pulls the water down. Now, farther down the valley, the water breaks through the ground, and that can be a fresh, natural spring water. You know, I find it particularly amazing that all the lakes and the rivers and the streams that we see at the surface, including the Great Lakes, the Mississippi River, and more, that represents less than 0.04% of Earth's near-surface water. That water, of course, is critical to our well-being, but it's a tiny fraction of the Earth's water budget. Now, the atmosphere holds perhaps 0.001% of Earth's water, mostly in clouds. Even though this amount is quite small, the water in the atmosphere has a huge effect because it cycles through very, very quickly. The atmosphere thus moves large amounts of water quickly and efficiently. Part of the reason that the Earth is such a dynamic planet is that water constantly moves from one reservoir to another. The hydrological cycle, like all these geochemical cycles, features complex and interconnected movements of matter. Parts of this cycle are experienced in a daily timescale, while other movements take thousands or even millions of years. So let's start with the oceans. The principal movement of water out of the oceans is through surface evaporation into the atmosphere. So the sun radiates down on the ocean surface with light energy, especially near the equator, and that energy causes substantial evaporation into the atmosphere. The atmosphere then transfers water vapor quickly from sea to land. And here's a critical point. Since the salts in the ocean don't evaporate, this process distills fresh water from salt water. That's why the ancient oceans are salty, but the lakes and rivers and streams on land are generally fresh. The ocean isn't just a passive basin of stagnant water, by the way. Water moves within the oceans as well. Ocean waters are layered. Deeper layers are generally colder, they're saltier, they're denser, and only the surface waters participate in evaporation. The surface waters are cycled relatively quickly, in some places in months or in years. But deeper waters are locked into the oceans for long periods of time, sometimes tens of thousands of years. Now, ocean water moves long distance around the globe through the action of currents. Look at this map. Surface currents move warm water from near the equator to higher latitudes. That happens, for example, in the Gulf Stream. That's here. It takes warm water from the Caribbean up towards the British Isles. Also along the temperate coast of California here. There, the water cools and sinks. It forms deep, cold currents that flow back toward the equator. In this way, the oceans play a major role in distributing heat across the globe. Fresh water is transferred from the atmosphere to the surface, primarily by rain and by snow. Even though the atmosphere only holds about 0.001% of Earth's water, it cycles that water so rapidly. In fact, the average residence time for a water molecule in the atmosphere is only a few days. It turns out that most rain falls back into the ocean, so that just moves water around a bit. But when rain falls on land, it replenishes lakes and rivers rather quickly. You know that's true if you live anywhere near a river or a lake where the amount of rainfall is variable. the water level and the flow rates can vary dramatically. But underground reservoirs are usually different. Rainfall can take hundreds to thousands of years to reach a groundwater reservoir. The process of percolation is often elaborate. It's very slow, so groundwater can't just be replenished by a single season of heavy rains. Now, of course, the flow of water from ocean to land through rainfall isn't a one-way street. The system of streams and rivers continuously returns fresh water back into the ocean. And again, this is a relatively fast return. The residence time of a water molecule in even the biggest river is typically no more than weeks or months. Then we have ice caps and glaciers, and they also participate in the water cycle. Snowfall adds to the net budget of ice and snow, and then you have melting and sublimation and breakup of ice sheets that subtracts. These processes are generally slow on human timescales, but major changes in the proportions of oceans and ice have occurred often in geological history, and they may be occurring right now. In 1998, an ice raft the size of Rhode Island broke off the Antarctic ice shelf. And there are recent studies that reveal that Greenland's ice cover is retreating quite rapidly, so we may be witnessing a period when the ice reservoir is diminishing and the ocean is increasing in size. There are times called ice ages. They represent a part of the water cycle that spans millions of years. An ice age is a period of geological history when a relatively high percent of Earth's surface water becomes locked into ice caps and into glaciers. The Earth's present ice caps began forming about 10 million years ago. For a long time prior to that, there were no permanent ice caps. Look at this. The ice caps reached a maximum extent about 2 million years ago, as shown in this map. Many times during the past 2 million years, the northern polar ice sheet has expanded south to cover much of North America and Europe, and then it's retreated in kind of a cyclical pattern. During the most recent glacial maximum advance, that was about 20,000 years ago, the sea level was hundreds of meters lower than it is today. Believe it or not, the east coast of North America was about 250 kilometers farther east, and a land bridge connected Alaska and Siberia across what is now the Bering Sea. At the height of these periodic glacial advances, as much as 5% of Earth's water became locked in ice. That's compared to about 2% today. We're now in a relatively brief period, an interglacial period, when there's a warming trend. But if humans don't disrupt the process too much, the present ice age may last millions more years. Some scientists are now arguing that human activities, especially the extensive burning of fossil fuels, which adds carbon dioxide to the atmosphere, that these human activities are causing a very abrupt change to this periodic pattern. I'm going to look at that possibility much more in the penultimate lecture of this series. You know, plate motions probably explain the formation of large ice caps 10 million years ago. As I said, their thick ice caps can only form when the continent is at or near one of the poles. And prior to about 10 million years ago, the continents were closer to the equator. And now, thanks to the changes that are wrought by plate tectonics, we're in a relatively unusual period when the Antarctic continent occupies the southern pole. And also, large portions of Eurasia and North America lie inside the Arctic Circle. So a lot more ice can build up now. Well, plate tectonics can help explain the larger scale ice ages over time, these periods of tens of millions of years. But why should glaciers keep advancing and retreating over periods of a few tens of thousands of years? A clever and convincing explanation for this periodic advance and retreat of glaciers, at least during the present ice age, was suggested by the Serbian civil engineer Milutin Milankovic. He lived early in this century. And the story of how Milankovic, who was an engineer, he worked on reinforced concrete buildings, how he came to study ice ages, is quite amusing. Now, prior to the First World War, Milankovic, like a lot of his countrymen, was caught up in nationalistic fervor. One evening, he was in a bar with a group of poet friends because they were celebrating the publication of a new collection of patriotic verses. And it turns out a wealthy banker at an adjacent table purchased 10 copies of the poetry book. The friends began to celebrate this unexpected windfall with bottles of wine. Well, after the first bottle of wine, Milankovic writes that he looked back on his earlier achievements and found them narrow and limited. And then after 3 bottles, he wrote that he had resolved to, quote, grasp the entire universe and spread light to its farthest corners. That's what wine will do for you. Anyway, he methodically set aside a few hours every day to study climate records. He even kept up this schedule as a prisoner of war during World War I. A member of the Hungarian Academy of Sciences arranged for him to have a desk after he promised not to attempt an escape. Well, Milankovitch explained periodic glacial advance and retreat as a result of orbital variations. They cause a slight shift in the amount of solar radiation reaching the northern and the southern hemispheres. And he saw three types of orbital variations that contribute to glacial cycles. These are the eccentricity of the orbit, the precession of the orbit, and the tilt of the axis. Okay, a major effect is a 100,000-year orbital cycle of changing eccentricity. The Earth is now in a very slightly elongated orbit, something like what's shown here. The Earth is about 1% farther from the Sun in June than it is in December. But the elongation of Earth's orbit is affected by the pull of other planets. It can be as much as 5% elongated. Here's a really exaggerated view, but you get the idea. As the orbit becomes more elongated during the next 50,000 years, Earth is going to experience greater seasonal contrasts in the Sun's energy, and thus more contrasting seasonal temperature changes as well. Okay, there's another orbital variation. That results from the precession of the Earth's rotation axis every 23,000 years. The average tilt remains 23 degrees. The orientation with respect to the Sun changes regularly over this period. Now, at present, the northern hemisphere is tilted towards the Sun during the summer months. But when the Sun is that's when the Sun's farther away. But in 11,500 years, the tilt will have changed so that the northern hemisphere is tilted toward the Sun in the winter months. And the net result is that the total amount of sunlight reaching the northern versus the southern hemisphere changes on this 23,000-year cycle. Now, this is important because the relative amounts of land and ocean are different in the two hemispheres. More ice can build up on continents. Now, a third, this is a more subtle effect. It's a 41,000-year cycle of axial wobble. Our present tilt is close to 23 degrees. Here you see the minimum tilt of 21.5 degrees. And the tilt varies from 21.5 to 24.5 degrees like this. The greater the tilt, the greater the seasonal contrast. Now, taken together, these three effects result in long-term 100,000-year glaciation cycles with short-term 20,000 and 40,000-year glacial maxima. My final point is that living things are part of the water cycle. Living things, including humans, require water to survive. Thus, while organisms hold a trivial fraction of all near-surface water, all life forms must develop a strategy to obtain a reliable water supply. Get this, a human being requires about 2 liters of water per day to survive. But listen, the average person in an advanced industrial society like the United States uses directly or indirectly about 6,000 liters per day. Think about that. You need 2 liters. You consume an average of 6,000 liters. How can that be? In what ways do you consume water in your life? Well, we use up to several hundred liters per day in personal activities. That includes drinking and cooking and, of course, showering and flushing the toilet and so forth. Still, that's nowhere near 6,000 liters a day. It turns out that most of the per capita usage is the result of irrigation for agriculture, as well as water for industrial processes. Agricultural pursuits in arid parts of the American Southwest are especially extravagant in their water consumption. The production of produce near the desert of Palm Springs and in the American Southwest are dramatic examples of this. If you eat fresh fruits and vegetables, then you're in effect responsible for the consumption of a portion of that irrigation water. And then there's paper and packaging. The manufacture of paper, for example, consumes large amounts of water as wood pulp is processed and transformed into white sheets. And the manufacture of cars, appliances, other products also uses lots and lots of water. So we all use lots of water. As the human population grows, we're faced with important problems related to water use. First and foremost is the problem of water pollution. Look at this. All water contains impurities because water is such an excellent solvent. It dissolves salt and all sorts of other chemicals, including harmful pesticides and heavy metals and lots more. In many regions, tap water contains high level of lead and arsenic, other dangerous substances. Old lead pipes and lead paint chips are one culprit, but we also throw away lead batteries and mercury thermometers and tons of trash that's left in dumps, and it's soaked by rainwater and gradually contributes to the problem. So think about what happens when it rains in a chemical waste dump. The water is an excellent solvent. Any chemical element in that dump may be dissolved and become part of the groundwater. Now, rivers and lakes, they can be cleaned up relatively successfully because the residence time of water molecules is relatively short. So cleanup effects, they have a pretty immediate consequence. But because groundwater reservoirs take hundreds or thousands of years to fill, today's pollution may affect water supplies for long periods into the future. A more immediate problem with groundwater reservoirs is overuse. One of the largest groundwater reservoirs in the United States is the High Plains Aquifer that underlies a large portion of the Midwest. This huge reservoir now provides about 30% of all water used for irrigation in the United States. The amount of water being withdrawn is much, much higher than the rate of refilling. Consequently, the water level has dropped dramatically and the water yield is declining. We're mining this aquifer dry and it may not last for much more than another 10 or 20 years. So what do we do when the aquifer runs dry? Well, first, let me assure you, we're not going to run out of water. We can always use desalination of seawater as they do in the energy-rich Middle East. But what happens when the price of tap water increases by a factor of 10 or more?